All right. Good morning. Let's quickly recapitulate again what we have seen last time. Yeah. We started. Synchronous counters. In that, we have seen an example where how we can reset back to any value. We have seen that, right? What else? That's it. Only one example we have seen, right? So let's take two more examples. Okay, we saw that that how do we create that? How do we design the counter? What was the usual procedure? Which counter we have seen? You tell me. Mod 9. Okay, in mod 9 counter using what? Using toggle flip flop, right? We said that we can implement this synchronous counters. We can reset back to any value depending on we have actually seen what is actually required, isn't it? We have seen that what is desired. Then depending on the present state and next state, we have decided what would be the inputs to those toggle flip flops. Not necessarily we have to go for toggle flip flops. We may use any flip flop, right? Let's take an example of a counter being implemented with a JK flip flop. So today is 3rd. So let's take an example of 3-bit counter. Now I should specify which counter. So I want it synchronous counters. Synchronous counter, up counter, using JK flip flops. Alright. We saw that this synchronous counter, we claimed that can be implemented using any flip flop. Let's see how that can be implemented using JK flip flop. First of all, it's 3-bit counter. Is there any specification like how it should count? Like yesterday we saw that it should count between 2 to 6, or it should count till mod 9 it should count till 0 to 8, and the other states will remain bracket, or we didn't care about what the other states were. What about the case here? What is the case here? 3-bit synchronous up counter means every other state is utilized. Okay, so there is no requirement of unused state is not there. Okay, so let's see how that can be designed. Let's go for what is desired. Let's draw the table first. Let me draw the states first. So what is the state? You tell me. 3-bit counter, no? So 0 0 0, it should go to 0 0 1 and so on, isn't it? 0 1 0 and so on. 0 1 1, 1 0 0, 1 0 1, 1 1 0, and 1 1 1, and it should go back to 0 0 0. Okay, whenever the next clock pulse comes. So this is a simple state transition diagram where on these edges I will represent a clock edge. Okay, now it is up counter, we may use positive edge trigger or negative edge trigger. Okay, so I will simply denote that 1 to indicate that the clock or the edge has arrived. And so on. So need not specify 1 because that is inherently understood. Now yeah, you tell me how many 3-bit is what is the first step you should do? First you should determine the number of states. Okay, the number of states or number of flip flops. How many? There is a 3-bit synchronous up counter. How many number of flip flops are required? 3. Which flip flops? JK flip flops. Okay, let's see. Then you should, the next step should be to note down the state diagram or state table. Okay, do that. State table. In the state table I should write the present states. What are the present states? Now it is 3-bit, so it will be Q2, Q1, Q0. The next states Q2 plus, Q1 plus, Q0 plus, and so on. And we have to decide what would be the input to those JK flip flops, right? So the inputs to the flip flops. How many flip flops are there? 3, right? So there will be 6 such inputs, right? So it will be J, J2, K2, and so on. J1, K1, and J0, K0. Alright, so let me draw this line. This is what is required, right? So now let me write down the states first. Now see here, if the present state is 0, 0, 0, yeah, let me be 0, 0, 0. What is the next step we expect? 1, right? Now for that, what should be the inputs to these JK flip flops? Okay. Now this the first bit, okay, the tooth bit, okay, the MSB is actually governed by J2, K2. This Q1 is governed by J1, K1. Q0 is governed by J0, K0. So we should set these inputs accordingly so as to get this 0, 0, 1, right? Now can you tell me what inputs of JKs will give you these states? Now let me first draw the table of JK. So what a JK flip flop does, I mean, if that is J and K, and let me write all the combinations: 0, 0, 0, 1, 1, 0, 1, 1. What happens when it is 0, 0, you tell me? No change, right? So no change. Here it will always reset the value, it will set the value, and here it will toggle, right, the complement. Now this is all Q plus, no? I mean the next state. Not the Q bar, okay, Q plus, okay, the first output of JK flip flop. Now you tell me, you have to retain 0, 0 at both of these flip flops, right? I mean Q2 is retained as it is, Q1 is retained as it is, only Q0 has changed, right? That means, so as to have this condition, okay, what we can do is, we have to set this JK as 0, 0, right? No change. Or we just want 0 at the Q, right? Where do we get 0 at only Q? We may have 0, 1 also, that is also possible. Okay, what I am saying is we can go for 0, 0 or we can go for 0, 1. Now why I am looking for alternate condition is because if alternate conditions are present, I can very well replace that bit by X or don't care, and that will be very beneficial in minimizing the circuit. Are you getting what I am saying? See, if you want this, if the current state is 0, 0, okay, if the current state is 0 and we want the next state to also be 0, so let me write that PS NS. So what is what are the JKs required? If present state is 0, next state should also be 0. There are two possibilities, right? I mean you can either give 0, 0 or 0, 1. That means I will write it as 0x. Is that okay? I mean it doesn't matter, you don't care what this bit is, compulsorily it should be 0 at the input, right? So let me write that as J and K. So So what this table indicates, let me write that. So this table indicates what values of J and K would satisfy these conditions, right? These transitions. Alright. Now let me complete that. So this is present state, next state. What is the value of, what are the values of J and K's? So let me complete that. Now you tell me, for if the present state is 0 and I want 1 here, you tell me. Now present state is 0. The next state I want it as 1. That means it should toggle, or you can set. You can toggle or you can set. So what is that? X1, right? What is that? I mean, you can complement the next state, right? Where is the complement happening? 1 1. Okay, so 1 1, and you can also set. Where is the set? 1 0. So what is the condition? 1. Because we don't care what this next bit is. Okay, the first input must be 1. Okay, that is what we expect. You complete that. 1 0 के लिए बोलो. If I want 1 0, okay, 1 0 can be obtained when the initial state is 1 and next state we want it to be 0. That means what? It should toggle. Toggle is happening at 1 1, or we can reset 0 1. You tell me what is that? X. Now this is, we don't care, X1. And what about the other one? I mean, if I want to retain the one state itself, what we can do? I can either retain using 0 0, or I can very well set using 1 0. What is that? X. Is that okay? How many of you didn't get this? You didn't get this. Okay, see you. In last class, what we have seen was asynchronous counters, right? Synchronous counters, my mistake. Synchronous counters, we saw that it can be designed using any type of flip-flop. That's what our claim was. And our prior attempt was using toggle flip-flop, right? How did we go for toggle flip-flop synchronous counters? We have seen an example of mod 9, right? Mod 9 counter. What we have done, we saw that what is the requirement. That means if the present state is such, what should be the next state? Okay, what we expect it to be the next state. Okay, and depending on what is the present state and what should be the next state, we predict what would be the inputs to those flip-flops. That is what we have seen last time. Okay, now that was for the toggle flip-flop, right, which was pretty easy. And now what I am saying is we can go for the synchronous implementation using JK flip-flop. Now for the JK flip-flop, we follow the same procedure. What is the, now I am going for an example of 3-bit synchronous up counter. In 3-bit synchronous up counter, if the present state is 0 0 0, we want the next step to increment by 1 and so on. We have seen that. Okay, so let's take the first step as 0 0 0. We want the next state to be 0 0 1. Okay, but we want to use JK flip-flop. So when can we obtain that 0 0 1? What should be the inputs to this JK flip-flops? Let's decide. How many flip-flops are required? First you tell me. There are 3 bits which has to be saved, right? 3 bits. So number of flip-flops will be number of bits, right? So 3 flip-flops are required. JK है ना, तो दोनों को दो इनपुट्स रहेंगे, तीनों को. Now what should be the input of J2 K2 so that 0 will be maintained? This is the state diagram or transition table for JK flip-flops. Okay, what does it say? When JK is 0 0, there won't be any change. When it is 0 1, it will be resetted. When J is 1 0, okay, JK is 1 0, it will set. When it is 1 1, it will complement. what we want, if the present state is 0, we want next state to be 0, retained as it is. There is no change. 0, 0, no? That is one condition. Okay, that is one condition. Okay, 0, 0. That means if the present state is 0, next state is also 0. 0, 0 can be one thing. Or we can also reset it very well. Present state is 0 and next state is also 0, na? Reset, na? So that happens with jk, jk as 0, 1. Okay. What do you want? The present state is 0, next state should be 0, always 0. Always 0 यहाँ पे है ना? What is the inputs required? 0, 1. That can also be possible because we don't have the present state is 0. Next state should be no change. Okay. So that is also possible with 0, 0. That means 0, 0 is one possibility, 0, 1 is another possibility. That means in general what? 0x. I mean we don't bother what the k is. Okay. This first bit should always be 0. That's why I have written as 0x. Is that clear now? Sure. I have completed that. Now we have seen the possibility for 0, 1. That means if the present state is 0, you want the next state to be 1. When is that possible? Either you should toggle the bit or you should set that bit. There are two possibilities. Either you should toggle. When is the toggling happening? This complement happens with 1, 1, right? When is the set happening? Another possibility set happening. You tell me here now. 1, 0. Okay. So what is that? 1x, right? Here you see. Is that 1x, right? 1, 1 is another. 1, 1, 1 is one possibility. 1, 0 is another possibility. So I am defining as 1x, 1x. Is that okay? Everyone? Oh. Let's complete this. Now, why I am going for multiple conditions? You got it? I want more don't case. Why I want don't case? Why I am caring about don't case? Just because we'll get a reduced and compressed, minimal circuit, and hardware can be minimized. All right. Now you complete it. So what is the jk value? You tell me. J2 K2. Bolo. 0x. Should I write 0x? You tell me here. 0x. Yeah, here 0, 0, 1. 0, 1, 1x, right? You simply copy this. Yeah, next. You complete this table 0, 0, 1. If the present state is 0, 0, 1, we want it next state to be 0, 1, 0, right? 0, 1, 0. Simply complete that. So what are the jk values? 0, x. What about here? 1x. What about here? 1, 0, 1, 0, yeah, x1. Yeah, and so on. You complete this quick. किसी को नहीं समझा अभी पूछ लो. Which one? Last one. See here. When is the x1? When present state is 1 and next state is 0. Here the present state is 1 and next state becomes 0. Earlier was the case when present state was 0 and then it was 1. That's the difference. Note down. 0, 1, 0. You tell me. 0, 1, 1. Bolo. 0x. Then 1, 1. x0, right? Yes, please. Which one? First one? Very first one. Okay. 0, 0. It should be 0x. Yeah, it's there. 0x, no? Barabar. J0 and K0. No, 0. Present state is 0 and next state is 1 here. So 0, 1, no? So it should be 1x, no? Which row you are saying? First, second, third? First, okay. Which column? Q0. Okay, it is changing from 0 to 1. We want 1, right? Either we should set the bit or we should complement. Either we should set the bit or we should complement. Complement is here or setting is here. What is that possibility? 1x. 1x. No, complement means not necessary. Whatever the present state is, it will complement. No, I'm still not getting. Yes, I mean the present state will be complemented if j and k is 1. So what this truth table indicates, you tell me? No matter how long you give these inputs, okay, it won't do the transition as long as the positive or the negative clock appears. Okay, you should always remember that. इसका मतलब ये नहीं कि 1 0 दे दिया तो आउटपुट वो आना ही है, नहीं, वो तब तक नहीं आएगा जब तक कि आप क्लॉक एज नहीं दोगे. We have seen that in the lab. You complete this table. Yeah, tell me these values, you please. So 0 1 1x. Yeah, rest. So it is 0 1 1 3 4 5 6 and 7, right? So here it would be 4 5 6 7, and you tell me here it should be 8. Wait, it should 3-bit counter, it should complete. Yeah, see here 1 1 1, next state should be 0 0 0. Now you complete 0 1 1x 1 0 x1. You tell me quickly, x1 here. Next x 1 1 na x 0 0 1 1x. After that 1 0 x1. Hope you are getting this. 1 1 x 0 1x. What else? x1 x1 and x1. Now see here how beautiful this is. We have simply taken note of what should be the input. I mean, we have also taken care of what should be the alternate inputs, okay, so that we can obtain that, these state transitions. And see what we have obtained, how nicely we have obtained. See here. Then now you should form. Now what was the next step? We used to find, we used to express the inputs in the form of the present state, right? In the present state, we need to express the inputs to the flip flop in form of we are representing the inputs of JK flip flop in form of the present state, right? Present state. So you form a flip flop. You form a K maps. How many K maps will be required? 1 2 3 4 5 6 K maps, right? You see here the job is simplified. See here. Except this. What is the pattern for this? You tell me. No, leave this. What is the pattern for this? What if all the inputs are alternatively x1 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 x1? What happens? What is the output? You tell me quick. What is the expression? Yes, it's 1. Confidently you should say that it's 1. Just because it doesn't matter what the x is, I'm assuming all x to be 1. It's 1, right? I mean, you can do that from the K map. So I'm drawing the K map for J0. What is that? See here. This is what? Q2, Q1, Q0, 0 0, 1 1, 1 0, 0 1. So what are the 1x 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 alternatively, right? So 1x, 1x 1x 1x. Is that okay? Where? Last third. This one? Fifth. Last button. This one? X? 1 is this 1 0 x1, yeah. So, yeah, my mistake there. So again, 2 are 1s, right? I mean, that's the advantage. So here it should be 1, no? Yeah, thanks for my correction. So it should be 1, no? So see here, now this is also getting served, right? I mean, this one will also be 1, isn't it? So you can form a group of all this to form 1. What was this? This table for what? J0, and you will also get the same thing, right? I mean, alternate 1s and x. Okay, x will be replaced by 1 and 1 will be replaced by x, but you will get the same expression as 1. You find the expressions for the other. Tell me quickly. Tell me the expressions, quick. Tell me for J1. Without drawing K-map also I can predict. You tell me. You should have that expertise, okay? Without drawing K-map you should be able to detect what should be the expression. 0 0. Yeah, J1 0 1 XX 0 1 XX 0 1 XX 0 1 XX again. Yeah, tell me the K-map. How should I group? This is the only possibility. Yeah, अब X बाकी है तो उसको ग्रुप जबरदस्ती नहीं करना है हमको, ठीक है? Tell me the expression. Huh? Q? Yes, Q0. Tell me for, now this is for J0, no? Oh yeah, sorry, J1. Tell me the expression for K1. Same? Sure? K0, oh sorry, K1 is Q0, right? And tell me about J2, K2. Q1, Q0. Q1, Q0. So J2 is Q1 and K2 is this okay? Correct? J2 is Q1, sure? Acha, Q1, Q0. Okay. And what about K2?
K2 is Q1, Q0. K1 is Q1, Q0.
Okay. J2 is?
J2 is Q1, Q0.
Q1, Q0. And what about J2?
J2 is also Q1, Q0.
Q1, Q0. Both are Q1, Q0. Verify. Alright. Draw the complete circuit. Draw the complete circuit. Okay. Now, we are sure that how these states will be behaving. Draw the complete circuit. Please do that. Draw the complete circuit. You can sit here. Sit here. बैठ जाओ. Now you can draw the circuit, okay? I'll leave it to you. You can very well draw the circuit, or you want me to. In this way you can design any counter. प्रेजेंट स्टेट ही तो डिटेक्ट करनी है, प्रेजेंट और नेक्स्ट स्टेट. ओके, आड़ा टेढ़ा भी पूछ लिया तो आपको आंसर करते आना चाहिए. ड्रॉ द सर्किट, कंप्लीट सर्किट. In exam, you should read the question carefully. Okay, I may ask any flip flop. I may go for D flip flop. Homework for you is to go for D flip flop implementation of the same 3-bit counter. Design 3-bit asynchronous up counter using D flip flops. Oh sorry, synchronous counter using D flip flop. ठीक है, asynchronous भी कर दो. दो होमवर्क. Draw the complete circuit, quick. Now you can go for any triggering, right? The difference would be, the output will be available at positive or negative edge trigger. I am going here for negative edge trigger. J0. Q0. Q0 bar, Q1, Q1 bar, Q2, Q2 bar, K2, J2, J1, K1. Tell me what is J0? What is J0? 1. It was always 1? Okay. So I will connect it to 1. Okay, it's synchronous, right? So the synchronous means it should have these clocks all connected to the master one. Yeah, what about J1? J1, you tell me. Q0? Should I connect directly? Simple. Bolo. J2? Q1? Q1, Q0. So there is an AND gate which is required. Is this okay? Then, yeah, K0, K1, K2, bolo. This K1 is Q0 bar. Oh, K1 is Q0, So I simply do like this. Is it okay? Then this one. K2 is Q1, Q0. I mean, we should simply short this, no? What about this? K0? Okay. Simple, no? That's it? Sure? Okay. Where should I take the output from? Where should I take the output from? Output कहाँ से ले? Q0, Q1, Q2, ना? That is what the present state is. So you should always take the output from here. So outputs will be here. These are not connected, okay? This is the connection, that is the connection. Q0, Q1, Q2. Mind it that, I am writing in the reverse way, okay? You should read the counter from the reverse. This is LSB, okay? Although I have written at the MSB position. Okay? Yeah, next. Take another example. Let's take another example. Example, write down, design a type T counter that means using T flip flops, right? Type T counter which goes the states like this: 0, 3, 5, 6, and back to 0, and so on. That means now here you should and okay, first note down this, okay. Now in the exam also, or wherever you have to design the counters, you first check what are all the conditions given or not. That means what are the conditions we expect. Okay, the counter should jump from 0 to 3. If the present state is 3, it should jump to 5. If the present state is 5, it should jump to 6. If it is 6, it should reset back to 0. But what if it goes to 1 somehow? Is there any condition given for that? No. Unless and otherwise specified, you may take it as don't care. Okay, we don't care if it goes to 1 or 2 or whatever the states, the remaining states which are not covered here. Okay, if it goes to 1, 2, let me write that, 1, 2, you tell me 4 and 7. Okay, if it goes to these states which are invalid, okay, we don't care. But if I specify that I want to reset the counter when the states are there, then you have to be careful. Okay, then there won't be don't care, there will be zeros involved there, or ones involved there, you don't know. Okay, you got what I'm saying? I'm saying that, see, these are undefined states here, so you may always go for X. Okay, we don't care about that. But if it is specified that we should reset it to 0 or maybe to 3, maybe 5, maybe 6, anything, then you have to be careful. Okay, so here I specify that reset the invalid state to 0. Note that. Okay, so reset the undefined state to, now it depends. Okay, I may specify 0, 0, 0, I may specify why should I specify that? Okay, I'm just specifying reset it back to 0. Okay, you tell me how many bits are required. Anyone? There are only 1, 2, 3, 4 states. No, how many bits? Only 4 states. Only 4 states. Okay, now you got me. See, as I said, the states are skipped here. You should be careful. You want to save 6. How can you save with 2 bits? You have to go for 6. So what is the maximum? That is 6, right? So you have to go for 3 bits at least. Design this. Go for it. First, step 1. You tell me. Step 1. Bolo. Step 1. Yeah. See what is desired. number of flip flops required. Tell me. 3. After that, step 2. Yeah, you should draw the state transition table. What type of flip flop? Toggle flip flop. डब्बे draw करके रख दो, table draw करके रख दो. Quick. And this way I can specify any count. should practice to draw the state diagrams. Draw the state diagrams. मतलब वो बोले निकालो 0 to 3, 3 to 5, 5 to 6 and back to 0. And this goal the state diagram should also include those undefined states. See here. Can you draw a complete state diagram? See here how it should be. 0, 3, 5, 6. Alright. Okay, I'll don't need to make so complications here. 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. So state diagram should be something like this. And there are various states here. 1, 2, what are those? 5, no? Oh sorry, 4, 1 to 4, no? Which are those? 0, 0, 1, 0, 1, 0, 4, 7. Oh sorry. We should go to so this is the complete state transition diagram. All right, tell me simply the values. Okay, now how to go for this? Now that okay, let me see your approach first. What are you doing? Now there are again I am saying that the treatment which I am using here, okay, that's not the only way to design such counters. You may come up with your own way. This problem itself, through multiple possibilities. You may design such counters in multiple ways. Okay, I'll demonstrate that with this problem. Anyone who has completed? Huh? Done? Done. Form the expressions. draw the diagram, first write down the expression and draw the diagram. So, the line is bold. Use paste. Click.
So I think you may come up with multiple approaches. Okay, you may consider all states in a single state table, or you may split the state table. Okay, you may worry about the defined states separately and undefined states separately, or you may consider all together. Okay, both of them together. So draw the circuit for both of them. Draw the circuit for both of them. The bar is very individually becomes X or operation. That means that in a इसमें तो इसको बड़ी मार देना चाहिए ये वाला कारण आप बड़ी मार देना ये हमारे ऑप्शन A bar, B bar is different from AB bar. Okay? De Morgan.
Click it here. Draw the line. Click here. Select that. Then you can drag. Click. Okay. We can simply write the expressions. No problem. Draw the expressions. Yeah. This is not a control. That is a galaxy, but we use the control. Yeah.
Yeah. You can very well take directly, okay? Inputs, if you are getting messy, okay? Inputs to the gate you can put directly in complicated or uncomplicated.
Divesh, you can go for writing the direct expressions. Okay?
Direct expressions.
Direct expressions for T2, T1, T0 with your.
So this table then, this table, do we have to write out?
No, they can easily get. I mean, we just want to verify with the others. Are they getting? So there's some 10 button here. You can write the expressions. T0, or you may T0. Change the color.
So are you getting these expressions, you tell me? With full implementation. I mean, if you are taking the valid condition and invalid states both into a single state table, are you getting these equations? How many you got it? Why? This row, yes. Why? This expression, are you getting this expression? Check. Look at it. क्यों समझ नहीं क्या आपको Alright, so you got with this approach. Now, how did you go for that approach? You have taken the valid conditions and invalid conditions, right? We saw that there was a condition mentioned that whenever it goes to invalid state, you should reset it back to 000. And we formed a table which was having the valid state and invalid state and the corresponding next state. And hence, we have defined what should be the input. The another way should be, okay, now the problem with this is, like, if it goes to invalid state, it has to go through multiple transitions to come back to the original state. There is no instant resetting which is happening with this approach. Okay, we haven't made use of any reset button there. But the another approach would be we can make use of that reset button which is usually there with the toggle flip-flop. So let's check for the conditions where the reset is required. Where is the reset required? For 1, 2, 4, 7. Okay, so we can form the combination or the circuit for this reset state separately and for the valid state separately. Okay, are you getting? So in that way you can very well form two types of, thanks Divesh,
you can form the table in two ways, right? That means, see here,